The next lesson we're going to have is in our unit on velocity and acceleration is going to be on acceleration. And in this unit, we're going to look at three things. We're going to look at acceleration, sort of what its definition is. We'll look at acceleration and distance, that is, how to find what distance an accelerating object travels. And we're going to look at simultaneous accelerations, what happens when you have objects that either have one acceleration, then a different one, or two objects that both have different accelerations and how that are in the same system. So let's look at the definition of acceleration. First thing is that when we talked about velocity in the last lesson, what we said was that an object has a certain displacement, a distance that it travels from its origin, and if you look at the rate of change, or the rate of that object's displacement, how much it changes by, and divide that by the time that changes, that will give you the velocity. It is basically the change in displacement over change in time. It's a rate of the displacement. If you do the same thing that we did with displacement to find velocity, with velocity, you're going to get an acceleration. And so here's our definition right here. An object's acceleration is the rate of change of an object's velocity. And so, or the rate of an object's velocity here. And so the acceleration right here is basically equal to the change. That's what a little delta, remember, means change. The change in velocity over the change in time. And so basically this is what we have here. A couple things to note. Number one, little vector symbols up here. Velocity is a vector, and so if you look at the rate of change of velocity, you will also get, that is a vector, you will also get an acceleration to be a vector as well. So acceleration is a vector quantity. Its direction does matter. This sort of makes some sense to you. If your car accelerates, it makes a difference which direction the car accelerates. If it accelerates forward, that's good. If you're trying to brake, you don't want it to accelerate forward. You want it to accelerate backwards or decelerate. Versus accelerating to the right or to the left. So vector quantity does make a difference. It has both a magnitude and a direction. Typically, in terms of most of the problems we're going to work out this unit, we are assuming sort of what's called a one-dimensional system, that objects can either go front or back. We're not going to worry about side to side yet. When we get to projectile motion later, we'll start talking about a 2D system where that's the case. But for right now, acceleration is a vector quantity. It has both magnitude and direction. But for this class, we're more commonly going to express the acceleration's magnitude, which we'll look at mostly, in terms of the original and final velocities, or A equals VF minus VO over T. And so in this case, A is the acceleration, T is obviously the time elapsed, VF right here is going to be the final velocity of the object, and VO is going to be the original velocity. All right? And so that's what we've got for these. So for example, if we had an object that started off at going 10 meters per second and ends up at 20 meters per second, it takes 5 seconds to do that, and we want to find the acceleration, we would say the final velocity of this object is 20, and that's not working very well. Let me get rid of that. So let's say the final velocity of the object is 20 meters per second minus the original velocity, which is 10 meters per second, divided by the time, which we said was 5, and that's not really reachable about, 5 seconds. And so 20 minus 10 is 10, divided by 5, which equals 2. And so we'd have our answer be 2 meters per second squared. Now, on that unit, meters per second squared, if you look at this, we're basically taking meters per second is a unit of velocity divided by a unit of time. And when we do that, that's basically going to be the same as meters over seconds times seconds, which is meters per second squared. This is the SI unit of acceleration, and the one we will use the vast majority of the time. All acceleration units are going to be in distance per time squared. Basically, so if you're talking about an acceleration of a car, sometimes you'll see that in miles per hour squared. You could have units of other types, but most commonly we will use meters per second squared. It's just, that's the SI unit, so that's what we'll use here. Now, let's take a look at an example here. Next one down here says, for an object near the Earth's surface, and this is something you sort of need to know about acceleration, just one value you need to memorize here. For an object near the Earth's surface, near or at, the acceleration due to gravity, which is usually given by lowercase g as its symbol there, is negative 9.8 meters per second squared. Basically what we're looking at here is that if I take an object and I drop it, it's going to accelerate downward due to gravity. That gravitational acceleration will not be the same in all places. On the Earth, for what people are normally around, we're pretty much all at or near the Earth's surface at all times. Acceleration to gravity is going to be 9.8 meters per second squared. If you're on the moon, it's definitely not going to be negative 9.8 meters per second squared. If you're on Jupiter, then it's going to be something vastly different than that even. So basically, this number right here, this negative 9.8 meters per second squared, is just a number that you need to know. Anytime you're talking about an object which is near the Earth's surface that is falling, that's going to be the acceleration. It's in free fall. That's the acceleration it's going to experience. So do note the fact it has a nice little negative sign out front. The reason why is because it says acceleration is a vector quantity, and so we need to have a direction. In this case, the direction is down towards the Earth, and so that's what we have there. So let's take a look and move a little onward here. Whoops, not what I meant to do. All right, so let's look at acceleration and distance. So we start off, say, an object with a constant velocity, that's zero acceleration, this is what we're going to start with here, is going to travel a certain distance, a displacement given by d is equal to vt. This is just a rearrangement of our good old-fashioned velocity equation, where velocity is equal to change in distance over change in time for constant velocities. Put the t up to the top, and what do you get? D is equal to vt. Same thing we have right here. And so let's suppose that we have some object which is moving at a speed, a constant speed of 5 meters per second. And it's going to do this for 9 seconds. And so if we do this, we would say the distance is going to travel. Distance is equal to the velocity, which is 5 meters per second, divided times the time, which in this case is 9 seconds. And so we get the distance the object travels is going to be 45 meters. Okay? Pretty straightforward, pretty simple math along these lines. But let's suppose we are going to look at this graphically. We're basically going to say, let's graph this on a graph, which as you can see over to the right over here, velocity versus time for a non-accelerating object, the constant velocity. So in this case, you can sort of see the red line shows that it's keeping a velocity of 5 meters per second for the first 9 seconds. And so we can sort of see that down there. Now, here's what we're going to try here. This shape that it makes, that is between basically the time of 0 where it starts, the time of 9 where it ends, the graph, the actual function, the curve that's on here, this red line, and between the axis makes a rectangle. And so you can see this nice little rectangle here. If you were to take this rectangle and you were to basically find the area of that rectangle, you would say, well, this side right here is basically going to be 5 meters per second, and this side right here is going to be basically 9 seconds. And if I was finding the area, I'd say length times width. And so my length is, we'll say 5 meters per second times my width, which is 9 seconds, and when I do that, I am going to get 45 meters. Well, what's that? 45 meters is a distance, and in fact, it's the same distance I got whenever I worked out my distance is equal to velocity times time. And so this is something that's sort of critical here, that the area underneath this curve gives the same value of the distance. If you have a velocity versus time graph and you basically find the area underneath that curve, that will tell you what the distance is. This is very similar to something we talked about last time. We talked about the slope of a distance versus time graph being the velocity. And our next lesson will deal with this, how areas and slopes sort of work together to let you find different things. But for right now, all we need to know is this, is that if you take a function, you take basically a velocity versus time graph, and you find the distance that the area underneath that graph, that's going to tell you the displacement or the distance the object travels. But this is only a case of an object that's not accelerating. What would happen if we had an object that accelerates? This line would no longer be straight anymore. We would no longer have just a nice simple rectangle. And so let's look at what happens if we have an accelerating object. And so in that case, this thing will let me click on this, which it does not seem to want to right now. So here, we have an accelerating object. So you can see it starts off way down here at 0 speed. It ends up right about at 6, it looks like. And so if we were to sort of do a little, ends up at 6 after 9 seconds. And so that's what we have here. Now, the same thing that we said before is still going to be true, that if I want to find the distance this object travels, I need to find the area underneath this section. But instead of being a rectangle anymore, this right here would be basically a triangle. and this triangle has half the area that the old one does. So the distance is still the area under the curve, but this time there's half the area. And so because there's half the area, what we're going to have to do is we're basically going to put a 1/2 out front of what we have when we're trying to find our distance for an accelerating object. Now, the two sides here. This side right here goes along here doesn't have a constant velocity. We can't just go ahead and put 6 in because it's not 6 all the time. Instead, technically what it really is here is this is basically the velocity as a function of time, v of t in good old function notation. And so that's what we have right there. Whereas this length right here is, well, up to there, is going to be the time. And so if we're multiplying these two together, we'd say it would be 1/2 times v of t, this right here, times time right there. But we know something about velocity. We said before that acceleration is basically the change in velocity over the time, the change in time. And so if we solve this for the change in velocity that goes on here, or sorry for a v here, we get that v is equal to at. Basically, if we want to have velocity as a function of time for an accelerating object, it's just going to be the acceleration times the time in that case, if we have a constant acceleration. And so whenever we're doing this, we know that v of t equals at. So let's take that at, plug it in for v of t, go it down here, and so we end up with distance is equal to 1/2 times at times t. At times t is at squared, and so we have a bit of a distance equation here, that for an accelerating object, the distance it travels is equal to 1/2 at squared. 1/2 the acceleration times the time squared. And this works great. If I have an object that basically is accelerating at a constant acceleration a for some time t, and it has an initial velocity of 0. But what if it doesn't have an initial velocity of 0? What do we have to do then? So in that case, basically, let's say, whoops, that was not what I meant to do at all. Let's say that basically, we look at that case, if I can get this set up right. All right, so let's look at that. So in the last case, we assumed the initial velocity, v0, v0, sometimes it's called either one, was 0. If it was not, then we'd have this guy that's on the right here. And so in this case right here, instead of starting at 0, this one starts at 3, right over there. Still ends way up here at 9. And so if we were to sort of sketch this out once again, we would see we've got down here and this right across there. The total area would not just be, in this case, d is equal to 1/2 at squared, because that's not the area. That right there, that 1/2 at squared, is the area of this triangle right here. But we said the rule is that the distance underneath the curve will give us, underneath the function, will give us the distance. The area underneath the curve will give us the distance. And so this is only part of it. If I wanted to find the rest of it, I would also need to find this section right down here that makes a rectangle. And so what I need to do is I need to add on a separate piece on this. And this separate piece will have the time as one part, and for this one right here would have whatever 3 is. And in this case right here, we said that 3 is basically equal to the original velocity. So VO, or V0, is equal to 3 meters per second in this case. And so this 3 is basically V0. And so I would need to basically have V0, this one right here, times my time down there. And so this is my sort of addition to the equation here, that to take it into account, I'd have to have that the distance is equal to 1/2 at squared plus v0 t. 1/2 the acceleration times the time squared plus the original velocity times the time. Now, if the original velocity is 0, this term just goes away. It just goes, boop, it's gone. That's if v0 equals 0. If it's not equal to 0, then I have to take it into account just like I do right here. You have to put it in. And so this is a little closer to what we're going to look for here for our final equation, but we also have left out one other possibility. What if the object did not start at 0 distance? In this case right here, let's suppose that when it starts, the time is 0. And so if it starts, the time is 0, then this t is a 0. Right? Whoops. That's not what I meant to do here. Basically what it means is that this t is a 0 right here, and that this t is a 0, and so both these terms just go away. And so 1/2 at squared is equal to 0, v0 t is equal to 0, and so the distance is 0. But what would happen if we had a distance that was not 0? What will we do in that case? Well, that's our next step here. Doesn't take a whole long to do it, but just a little bit here. And so, taking into account the fact that an object's initial distance is not always 0, we need to add an initial distance term. Initial distance is going to be d naught. That's going to be, let's put it on the end. And so we get this equation right here. This is our big distance equation here. So basically, d is equal to 1/2 at squared plus v naught t plus d naught. Between this and our acceleration formula, final velocity vf minus VO over T. These are the two biggies. These are the two ones that you need to make sure that you know, at least be able to apply, because everything that we're going to do, at least for the near term, for most of the rest of the year, is basically going to be a use of one of these two equations, because between these, and I guess, yeah, these are the two big ones. Because even if you have an object that's not accelerating, you basically can get that out of this. So note if the acceleration and the initial distance are 0, this turns into our regular constant velocity distance equation. So we get d is equal to 1/2 at squared plus v naught plus d naught. But if our original distance is 0, boop, that's gone. If our original velocity is 0, boop, that's gone. And sorry, that's not right. I didn't mean to say that one. Correction, undo that. We didn't say the original velocity was 0. We said the initial distance is 0 and the acceleration is 0. If the acceleration is 0, this term goes away. And so we get distance is equal to v naught t. And if it's not accelerating, then your original velocity is the same as your final velocity. It's just your velocity. And so d is equal to vt. And that's one we've seen before here. Rearrange it. You got v is equal to d over t. Good old-fashioned velocity equation from way back when. So these two equations right here, especially this distance equation, is one you need to make sure that you know. At least be able to access it whenever you need it. So let's move on and do a little bit of application on this. So a ball thrown up in the air with a speed of 15 meters per second will travel how high? Well, first thing we need to recognize here is if you're throwing a ball up into the air, you are probably on Earth. And if you're on Earth, that means that the acceleration due to gravity is going to come into effect here. And so this ball being thrown up in the air will have an acceleration of negative 9.8 meters per second squared. And so we're going to start with that. And so with this, let's set up our acceleration equation. We say it's going to be acceleration is negative 9.8 is equal to the final velocity. Now, how high will this thing go? Well, that's what we're trying to figure out here. But we know this. If you toss something in the air, when it reaches its highest point, it turns around. It goes from going up to going down. And at that highest point, it has a velocity of 0. And so the final velocity of this object is 0 minus the original velocity, which it tells us, 15 meters per second. Speed technically, but since we know he's throwing up, the up and the 15 go together to tell us we have a velocity here, direction and magnitude, divided by the time, which we do not know. And so this could let us figure out the time. And so when we plug this in, we basically go ahead and multiply the t over, so negative 9.8 t, that's an 8, equals negative 15, divide both sides by negative 9.8, negative 9.8. And so in doing that, we get, put in the calculator, t is equal to 1.5306 seconds. Okay? And so once we've got that, we're trying to figure out how high will it go. That's a distance. And so to find a distance, we'll need our distance formula. D is equal to 1/2 at squared plus v naught t plus d naught. And so to find this distance here, we're going to plug it in. Distance we're looking for is equal to 1/2 times the acceleration, which is negative 9.8 because it's on Earth, times the time squared. Time is 1.5306 squared, plus the original velocity, which we're told was 15, times the time, 1.5306, times the original distance. In this case, it's being thrown from the ground. Here's the thing about original distance. You basically get to pick where your 0 is. You could choose to say, I'm going to throw this from original distance of 3 meters, or 7 meters, or 7,000 meters. But usually you're probably going to want to pick his initial spot to be 0. Sometimes, like I say, if you're throwing this off a building that has a certain height, you might want to pick the original distance to be something other than that. But you get to pick the original distance, but once you pick it, you have to be consistent through the rest of your calculations with that value there. And so I'm going to say in this case, I'm throwing it from the ground. The spot that it basically is, it's leaving my hand is 0 on this. And so I don't have any original distance. I just have this right here. And so doing that, I basically solve this out, and when I get this, I end up with 11.479408 meters. Significant figures, I got 15 right here, so this would be 2. So my final distance is basically 11 meters. So this ball would go 11 meters high. That's basically how you would do a simple problem like this. So let's take a look and move on to another one on this. Still ignoring me, I see. So an apple falls from a branch 12 meters high. With what speed will it hit the ground? Sort of a Newton problem here. And so I have a branch with an apple on it. I don't want a blue apple. I'll go for a red apple. And so I've got my apple right here, which does not look like much an apple because it got smashed against the board here. And I know that it is going to fall a distance of 12 meters. Now, to set this up is that I know it's 12 meters high. Do I want my 12, where do I want my 0 here? Because I'm going to use my distance equation, but I need to figure out where my 0 is going to be. I could call this distance 0, or I could call it 12. Same thing with here. I could call that distance, if I call this distance up top 0, that bottom distance has to be negative 12. What it ends at, my final distance, would be negative 12. If I call my top up here 12 meters, which I think I am going to do, then that's going to mean my bottom is going to be 0 in this case. You just have to pick one and you have to be consistent. So could put 0 at the top and negative 12 at the bottom, or could put 12 at top and 0 at the bottom. Doesn't matter, just as long as you pick one and stick with it. So this is what we have. So let's set this up for the rest of this here. So we know that we have that the starts off at 12 meters, going to end at 0, and so that means my final distance is going to be 0 is equal to 1/2 times negative 9.8 times t squared, which I don't know, plus the original velocity, which is, in this case, we're dropping it. It's 0. It's not there. And so I can leave out that term because since I'm dropping it, it has no original velocity, plus the original distance. In this case right here, I decided the original distance was going to be 12. That's how I set this up. So this is what I have to start with here. And so plugging this through, I move the 12 over to the other side, so I get negative 12 over here is equal to 1/2 times negative 9.8, which is negative 4.9 t squared. Divide both sides by negative 4.9, and I get, let's see, t squared is equal to, 2, that's a 2.44898. Got to take the square root of that, and so doing that, we get that t is equal to 1.56492 seconds. So I have my time on this. And so the question is, what speed? This gives me time, but doesn't tell me about speed. So I'll have to use the other acceleration equation. Our good old acceleration is equal to Vf minus Vo over t. I know my acceleration is 9.8, negative 9.8, because it falls downward, equals the final velocity, which is what we're looking for, minus the original velocity, which we dropped it, so it's 0, divided by the time, which I just found is 1.56492. Remember not to round till you get to the final answer here. And so in doing this, I basically can just, it's pretty standard math here, so 1.56492 times negative 9.8. And so for that, I get that my final velocity is equal to negative 15.33 meters per second. And significant figures would be 2. And so my final velocity here is going to be negative 15 meters per second. Note that it is negative. That makes sense because it is falling downward. And so whenever it hits the ground, it should be going down at that point. Now, one quick just sort of general note. It says with what speed will it hit the ground. Now, some of you will say there's a common sense answer to this. 0. When it hits the ground, it stopped. In physics sense, when we ask the question with what speed will it hit the ground, we're asking about what speed will have the instant it first touches the ground. And so that speed right there is basically equivalent to saying what speed is at the instant before it touches the ground. We're asking questions about what happens before that extra force of the ground hitting it interacts with it. It's just basically what happens, will it have the instant before it hits the ground? And so that's really what this question's asking for. When it says what speed will hit the ground, what speed will it strike something else, it's asking about what speed will have the instant before it does that, really. Just to sort of address that particular qualm that always comes up on things. So let's see what we've got for later on here. So, a car traveling at 25 meters per second, brakes, stopping at 150 meters. How long does it take the car to stop? So, in this case right here, is that we know the distance it takes to stop this car is 150 meters. And so, let's go ahead and set up our distance equation. So, 150 is equal to basically 1/2 times the acceleration. Do we know the acceleration? This is on Earth, because it's a car, but this car is not in free fall. So we wouldn't want to use negative 9.8. We're just going to have to, we don't know the acceleration of this car, so we just have to call it A. And then the time, well, we don't know that, so we're looking for t squared, plus the original velocity of the car, which is 25, times the time. The original distance of the car, basically in this case, we're going to say that's 0. And that's the reason why he ends up at 150 later. We could have chosen the original distance to be 150 and the final distance to be 0. That would have worked just as, actually, I guess the original distance would have to be, in that case, negative 150 because he travels forward by 150 meters. But it's up to you. It's going to be easiest to take your original position as 0 in the vast majority of cases. So this is what we have here. The problem is with what we've got right now is we have two variables. We have both an acceleration and a time, and so we cannot solve this as it is. And when this happens, basically what you have to do is you're going to have to go ahead and put the other equation out and see if that helps you out. So acceleration, which we still don't know, is equal to final velocity. Final velocity of this car is 0. It's stopping, minus the original velocity, which we're told is 25, over time. Well, that also only has two variables. We can't solve that one either. But here's going to be your friend in a lot of these, is that whenever you have a case like this, we have now two equations and two variables. Substitute and solve. And so for this one right here is that we've got that the acceleration is equal to negative 25 over t. And since that's the case, what we can basically do is we can plug that into our original equation here. And so if we do that, we get that 150 is equal to 1/2 times our acceleration, which we just found. Acceleration is equal to negative 25 over t. Negative 25 over t times t plus 25t. Okay, and so in doing this, we get 150 is going to be equal to basically 1/2 times negative 25, and so that's negative 12.5. So negative 12.5 t, because this t and that's t squared up there, this t and that t squared cancel, and so we just have t on the end here, plus 25t, like that. And so 150 is going to be equal to 12.5 plus 25 is just, negative 12.5 plus 25 is just 12.5. So 12.5t, divide both sides by 12.5. And so it cancels over here. 150 divided by 12.5 should be 6. I'm doing this in my head right. So I get a time is, sorry, not 6, 12. Not thinking 25 goes into 150 6 times. But 12.5 goes in 12 times. 12 seconds. And so I get 12 seconds here. And so the question is, how long does it take the car to stop? It takes the car 12 seconds to stop. Significant figures, I've got 2 right here, 2 right here. So my answer is just 12 right there. So that's how you go ahead and working out one that happens like this. Now, what if we had a case where we had a problem that had something that the object had more than one type of acceleration? A little bit of a longer, more complex problem here. Simultaneous accelerations. An airplane on a 3,000 meter runway has a takeoff acceleration of 2.2 meters per second squared and a takeoff abort braking acceleration of negative 3.7 meters per second squared. Basically what we're saying here is that the airplane takes off when it's on the ground at 2.2 meters per second until it takes off. Once it's in the sky, it doesn't really matter anymore. But if something goes wrong and they can't take off, they have to basically hit the brakes, put the engines in reverse. And when they do that, they can, in this case, have a maximum acceleration of negative 3.7 meters per second. It's a deceleration. That's the reason why it's negative here. Question is, how far can the plane go down the runway and still be able to safely abort? So we're basically talking about the point of no return. There is some point along this runway where if the plane were to try to brake, they would not be able to successfully do it without going off the end of the runway. And so the question is, what is that point? So in this case, we really have sort of two sections of things going on here. We have an acceleration section along the first part of the runway and a deceleration section along the second part of the runway. And so let's set up an equation first for this first section on the runway. And so to do that, we're basically going to say that this distance right here for the first section, d, is going to be equal to 1/2 at squared. So 1/2 times the acceleration of the first section, which is 2.2, 1/2 times 2.2 times the time squared plus the original, and we're going to call this actually t1 in this case because there are two times here. There's a time of acceleration, there's a time of deceleration. All right, so plus the original velocity. In this case, they're taking it off. The original velocity is 0 here. So that term goes away. Original distance is going to go away for the purposes we have right here. And so we have this. D is equal to 1/2 times 2.2 times t1 squared. Now let's look at the next case, which is going to be basically our second one, and that plane is going to go a distance which is not the same as the first plane's distance. To stop right at the very end of the runway, which is the farthest they could go, the second distance is going to have to be the difference between the first distance, d, and the length of the runway, which is 3,000. And so the distance that one will go will basically be 3,000 minus d. And that's going to be equal, that's your distance it travels, is going to be equal to 1/2 times the acceleration, which is negative 3.7, times the time squared. In this case, it's going to be t2, because this is the second one here, plus the original velocity. In this case, this does have an original velocity because basically this plane gets up to its top speed and realizes, oh, this isn't going to work. Hit the brakes. And so it has a top speed here, which is going to be the final speed of the original section, but we don't know what that is. I'm just going to call it v right here, times the time. And we've already taken the distance parts into account, and so this is the time. Now there's a time 2 because this is the second part here. So we have two equations currently, but we have, let's see, look at the variables. We have d, t1, t2, and v. 4 variables. Ouch. Only 2 equations. This can't be solved as it is. We need at least 2 more equations. Fortunately, we have 2 more equations. Look at our acceleration equations. So this one right here, 2.2, is the acceleration is equal to the final speed. In this case right here, the final speed is that v that we talked about, minus the original speed, which is 0, over the time t. We've got that right there. Our next one that we've got over here is that we know the acceleration is 3.7 meters per second, equals the final speed, which final speed should be 0 here because we're trying to stop, minus the original speed, which is v, because that's what it was going at the end of the first section, divided by the time, t2. Now this one should be a t1 back here. Okay, so now we have 4 equations and 4 variables. This is solvable. You may not want to solve it, but you can solve this here. Keep in mind that at this point it's basically algebra the rest of the way. If you do have a technique for solving equations other than the one I'm going to use, other than basically this is a substitution method, you may use that technique. That's up to you. So there are certain calculator programs that will basically do this substitution at this point. I trust if you're in this course you basically know how to do algebra, and so I'm not worried about the fact that if you choose to use basically an online or a program for solving simultaneous equations, that's fine. That's understandable, because it can get to be a little annoying to have to work out significant equations here. You need to make sure you know how to do this, but once you're certain on the algebra part, is that the setup is the important part from a physics standpoint. Can you set up the equations? If you can solve them, you're good. So let's go ahead and we'll just work this out, see what we'd want to do on this. So first thing we can say is let's look at the first 2 equations. D is equal to 1/2 times 2.2 times t1 squared, and the second one, 2.2 equals v minus 0 over t1. There's a t1 in both equations, so let's solve the second one for t1 and then plug it into the first one. So we basically get over here that v is equal to 2.2 times t1. And so then that would give us, for t1 to solve for that t1 is equal to v over 2.2. At that point, we can plug it back into the original equation here, that d is equal to 1/2 times 2.2, that's just 1.1, times t squared. In this case right here, t1 squared, we said was v over 2.2. So that's v squared over 2.2 squared, like that. And so when we work that out, we get the distance is equal to, I get 0.227 v squared is what I get for that distance right there. Now let's look on the other side. On the other side, we can do sort of a similar thing, is we can rearrange this negative 3.7 equals negative v over t2, solve for t2. That would give us that t2 is equal to v over 3.7. So t2 is equals, move the t2 up and then divide the 3.7 down, so v equal over 3.7. The negatives cancel. So we have this. Now we can plug that into the one up top. So I get that 3,000 minus d is equal to 1/2 times negative 3.7, which is negative 1.85, times t2 squared. T2 is v squared over 3.7 squared, plus v times t, and or v times t2, which is v over 3.7. That's a 3.7. And so in doing this, we basically should end up here with, let's see, work this out here, because it's negative 1.85 divided by 3.7 squared, and that's a v squared, and so is there v squared on this side, so plus 1 over 3.7. And so I get in this case that 3,000 minus d is going to be equal to 0.135135 v squared, like this. Now at this point, I have two variables. I have a d and a v. But over here on the other side, I also have a d and a v. So I can just solve, I've already solved this side on the left for d, so let's plug that in. And so I get 3,000 minus, instead of d, we'll do 0.227 v squared. 0.227 v squared. Technically shouldn't be rounding anything here, but we are simply because of just space reasons. 0.135 v squared right here. And so when we solve this out, we get, if you solve for v here, let's see, so we'd say add 0.227 v squared to both sides, so that it ends up being, let's see, 0.362. Then so you divide that by 3,000, end up getting v squared, and then square root of that, and we get that v here is basically 91.02 meters per second. So what we just found right there is basically how fast the plane ends up going before they hit their brake. They accelerate full bore, and then once they hit that, if they go any faster than that, they'll basically be too far to go off the end of the runway. But the question is, how far down the runway do they go? And so I've got to get from v to d. I'm looking for really the d right there. That d doesn't have any v's in it, though, for that equation. So I'm going to have to put it into the one that's below it, right down here, and then use that to find the t, and then solve out that. So I would say right here that 2.2 is equal to the velocity, 91.02, over the time, t1. And so solving this, we get that t1 is equal to, let's see, multiply t1, 91.02 divided by 2.2, 41.37 seconds. And so 41.37 seconds, plugging it back into our original distance equation. Distance is equal to 1.1, 1/2 times 2.2, times t squared. So t is 41.37 squared. And so in doing that, I get that a distance is 1.1 times 41.37 squared. The distance is 1,882, pretty much, meters. Significant figures technically should have 2, so actually our final answer would actually be 1,900 meters for this right here. But, so, this is an example of a fairly complex acceleration problem that basically you take the distance of this, in this case, so basically this plane can go 1,900 meters before they need to hit the brakes. If they waited longer than that, they will go off the end of the runway, even at best case scenario. So that is an example of how you would do a simultaneous acceleration equation. Cases where you have multiple accelerations, you basically simply set up a system of equations. And once you have that system of equations, substitute and solve.